Hello, today's lecture we will be discussing about piezoelectric transducers. So let us first see the structure of a piezoelectric transducer, then we will go and see the more details about the mathematical relations and equations behind the piezoelectric transduction process. So the picture indicates these are two metallic plates that is separated by piezoelectric crystal. So this is a piezoelectric crystal which is made up of either by the naturally available piezoelectric materials such as quartz or Rockwell salt, or it could be also by using the synthetic types like lithium sulfate, ceramics and many other types of synthetic type or the artificial type of piezoelectric materials. So these two plates, there are two plates, which is the top metallic plate and bottom metallic plate, and in between you will find a piezoelectric transducer. So piezoelectric phenomenon, it is also called the electroresistive phenomenon, where when an external force is applied, on the piezoelectric material, there may be a, depending upon the nature of the force, there may be a displacement. For example, if you are going to compress the crystal, definitely it is going to change the dimension. For example, in this case, the thickness will change. So assume that we have a thickness of let us say T, and this T can be plus or minus delta T. So minus delta T happen when there is a compressive force is applied, and plus delta T is going to happen when there is a tensile force is applied. So if you are going to apply tensile force, it will be in one direction, and if you are going to apply compressive force, it will be in the other direction. That is why this type of piezoelectric behavior is like what, having a direction sensitivity. Means what, depending upon the nature of the applied force, the voltage will also will change. So in this particular example, this is a T. We are assuming that T is the steady state value, or the value when it is neutral state, and delta T is nothing but it can be the expansion or maybe the contraction, depending upon the nature, can be plus or minus delta T. So the main purpose of these applications of these piezoelectric transducers, when there is an external force is applied, then this displacement causes some changes in the material. That change in the material will cause or will rise to a output voltage. In other words, these are the sensors that can be used, or these are the transducers that can be used for transforming vibrations into electrical signals and vice versa. So if you are going to apply a voltage across the metallic plates, then a corresponding dimensional changes will appear. So there are many practical applications of this type of transducers. One of such application is used in ultrasound scanners, whereas by applying high frequency signal across the piezoelectric material, it is possible to vibrate the piezoelectric crystal at a very high frequency, and this is nothing but vibrations like a sound signal, and this sound signal can be used for diagnostic purposes. So the piezoelectric transducer is exactly similar or looking like a capacitor, because the principle is also something like a capacitor, because in the case of capacitor we have two plates that is separated by a dielectric. So in the case of dielectric, in this case that dielectric is replaced by piezoelectric crystal or the transducer. So let us see the mathematical relations associated with the piezoelectric transducers. As we have already said, these are the transducers which are capable of transforming mechanical vibrations or mechanical forces into electrical signals and vice versa. So when there is a mechanical force which is applied on the crystal, there must be some voltage that will be developed because of the displacement. So that voltage across the piezoelectric transducer due to the deformation is obtained by the relation Q upon C, where Q is the charge in Coulomb and CC capacitance. Now, Q is also obtained by the relation D times F. So, here D stands for the charge sensitivity, which is normally a constant, it's a material specific term, and F is the force which is applied in Newton. So, this force F, which causes changes in the thickness of the material. In this particular example, it is thickness, but in other cases could be it can be length or can be width or it depends, in which direction the force is applied. But in this particular case, we are assuming that the thickness is changing. All right. Then the corresponding thickness, change in thickness, which is assumed to be delta T, and T is the original thickness. So, delta T upon T will give you the strain due to the applied force. So, that F can be calculated by the equation F is equal to AE delta T by T. So, this is the strain part, and E stands for the Young's modulus or the modulus of elasticity, which is nothing but the ratio of stress by strain in the elastic range of the material, and A is the area of cross section. So, if you substitute the unit, the area in meter square and the Young's modulus in Newton per meter square, so the meter square get cancelled, and delta T, this will be a unitless quantity. So, in the end we will get F in terms of Newton. The elasticity, the modulus of elasticity or the Young's modulus E is calculated by the relation stress by strain. So, stress is nothing but force upon area. So, force on area F divided by A. Strain is calculated by the equation changing the dimension to the original dimension. In this case, it is thickness, so del T divided by dt, del T divided by T. So, if you substitute the value or if you rearrange the equation, we will get E is equal to Ft divided by A times delta T or del T. Now, where F is the force, T is the thickness, A is the area of cross section, which is calculated by the equation. Not the area of cross section, supposed to be area of the crystal, and that is calculated by the equation area is equal to W into L meter square. So, by substituting the value of F in the Q equation, Q is equal to D times F. So, if you substitute this value of F, we will get Q is equal to D into AE del T by T in coulombs. So, now the change in Q, that will give rise to a voltage V out by the capacitance principle. V out is equal to Q divided by Cp, where Cp is the capacitance between the plates or across the the piezoelectric material or the piezoelectric crystal. So, Cp, that is calculated by the equation epsilon 0 epsilon r A divided by T, where T is the thickness, A is the area of cross section. Okay, so we know that this V out is equal to Q divided by Cp, and Q is the charge. That charge is due to the applied force, that can be calculated by the equation Q is equal to D times F, and Cp means what is the capacitance of a parallel plate capacitor, which is calculated by the equation epsilon 0 epsilon r A divided by T. So, if you substitute this equation, we will get dt divided by epsilon r into F by A, and F by A is nothing but force by area, which is nothing but pressure or stress, which is in Newton per meter square. So, the above equation can be simplified as V0 equal d divided by epsilon 0 into epsilon r into T into P, where T is the thickness and P is the pressure or stress, d divided by epsilon 0 epsilon r, these are all constant. So, this term d divided by epsilon 0 into epsilon r for a certain material is going to be constant, and that constant is referred as G. So, V0 can be written as G into T times P, where G is d divided by epsilon 0 into epsilon r, and it is called the voltage sensitivity of the crystal. Now, the voltage sensitivity can be calculated separately. For example, if you are finding the value of G from the previous equation, G equal V0 divided by P times T. And if you are going to rearrange the equation, V0 divided by T divided by P, V0 divided by T means voltage divided by distance, which is nothing but electric field. So, electric field is the field produced by like a plate. If you are looking at this particular case, we can find that there are two plates where we are going to apply a voltage. So, when we apply a voltage across two plates, then there exists an electric field, and that electric field is calculated by the equation V0 divided by T, where T is the thickness. So, this will give a relation for G is equal to what? E0 divided by P. E0 is the electric field in voltmeter, and P is the pressure or the stress that we applied. Okay, now the charge sensitivity of the crystal, which is already we have mentioned at the beginning of this lecture, D, which is calculated by the equation epsilon 0 epsilon r into G. So, G is the voltage sensitivity, whereas D is the charge sensitivity. Now, let us see two different materials, like one is a natural crystal and other one is like an artificial or synthetic crystal, and we will see the value of G, epsilon and D. Already we have said G is the voltage sensitivity, which is millivolt per Newton. For a quartz, we found that it is 50 into 10 to the power minus 3, and the epsilon, which is the permittivity in farad per meter. For quartz, it is 40.6 into 10 raised to minus 12, and D, which is the charge sensitivity in picocoulomb per Newton, which is about 2. In the case of barium titanate, G value is 12 into 10 raised to minus 3. Then the epsilon value, which is the permittivity, is 12.5 into 10 raised to minus 9, and the D value, which is the charge sensitivity in picocoulomb per Newton, which is 150 in this case. So, in this part we are going to see the typical modes of operation of piezoelectric transducer. The first diagram shows that it is a thickness compression. The force applied to this crystal is compressive force. As a result, thickness is going to be reduced, so there is a compression is going to happen. So, this will give rise to some potential. Then the same manner, this is like a elongation, thickness elongation. In this case, thickness elongation, actually the force is applied is a tensile force. As a result, the thickness is going to be increased, and this force is like a shear force, but acting along the phase. So, this is going to induce some kind of phase shear, and in this example, this is like a thickness shear. We are going to apply the shear along the thickness. So, these are some examples for the modes of operation of this type of transducers. There are many other modes. Also this device can be operated. So, now let us see the equivalent circuit of piezoelectric transducer. So, there are two equivalent models are there. The first model is based on the Q model, which is the charge model, and another is based on the voltage model. So, it is like a parallel circuit, whereas this is a series circuit. Now, this is the Q, which is the charge, Cp is the parallel plate capacitor, and Rp is the corresponding resistance of the plate. So, now this is like a parallel circuit, and we will have the output at this side, whereas in the case of voltage circuit, the voltage source is here, then there is a series capacitor followed by a parallel resistor, which is a plate resistor, which comes across the output terminals. Now, when we connect the piezoelectric sensor to an output circuit, then definitely there may be some effect of loading will occur. So, that can be calculated using the equation, I mean the diagram here. This is the earlier circuit, and RL is the load resistor that is supposed to be connected across the sensor. Now, the major issue is the capacitance effect actually. So, there are capacitance, it could be due to the load capacitance, because of the load itself, some effect of capacitance effect may come. We will also having issues of the capacitance of the cable, and there may be stray capacitance or any other capacitance due to maybe some external field or something. So, all together can be represented as CL. So, CL normally comes across the RL terminal. So, now the circuit consisting of RP and RL in parallel. RP is already, we said this is a plate resistance, is also called the leakage resistance of the piezoelectric transducer. Now, the value of RP is much higher than the value of RL. Therefore, we can further simplify this particular diagram as follows. So, here RL represents the load resistor, CL is the leakage or the load capacitance, and the combination of the other type of stray and cable capacitance, and CP is already we discussed the parallel capacitance of the device. So, this is a simplified diagram by considering the effect of the load resistor, so now let us try to find out the load impedance ZL, which is nothing but the parallel combination of RL and ZL. So, RL into 1 divided by j omega CL divided by RL plus 1 divided by j omega CL. If we simplify, we will get a relation RL divided by 1 plus j omega RL CL. So, let us try to look at the total impedance of the piezoelectric transducer ZO, which is nothing but the series combination of CP, the impedance of the CP, and the parallel combination of RL and CL. So, already we found the value of the output impedance. This output impedance will add to the impedance of the CP, that will give you the total impedance. So, Z out is equal to 1 divided by j omega CP. The CP is nothing but the capacitance of the parallel capacitance, and this value we already found it for the parallel load. Now, if you simplify the above equation, we will get 1 plus j omega RL into CL plus CP divided by 1 plus j omega RL CL into j omega CP. The voltage across the load that can be calculated by the equation VL is equal to V0, which is the generated voltage, multiplied by ZL divided by ZO. ZL is the load resistance, load impedance, and Z out is the total impedance. So, if you calculate that, V out into ZL is already calculated, which is a parallel combination of RL and CL. As per the earlier discussion, RL divided by 1 plus j omega CL into RL into, we want Z out. Z out is already calculated, but we want 1 by Z out. So, if you substitute the same equation that we found it in the previous slide, Z out. So, we will find omega Cp into 1 plus j omega Cp RL divided by 1 by j omega RL into Cp plus CL. If you simplify this equation, some of the terminology, some of the terms will get cancelled, and you end up with a result V0 into j omega Cp RL divided by 1 plus j omega Cp plus CL into RL, and this of course is a complex term. So, we try to find out the magnitude term that is calculated by the equation V0. The j will get over because of the magnitude omega Cp RL divided by, since we have the real term and the imaginary term here, so we have to square and under root. So under root 1 plus omega square Cp plus Cl whole square plus RL square. We already discussed in the past, the change or the voltage generated in the strain, what you call the piezoelectric transducer is calculated by the equation the D into F divided by Cp, where we call the D is the charge sensitivity. So that is multiplied by the applied force divided by Cp. So this V0 can be replaced by this equation dF divided by Cp, where Cp is the parallel capacitance. So if you are going to these two terms, for example, the Cp will cancel with the Cp, and hence we will end up with a relation D into F omega RL divided by square root of omega square into Cp plus Cl whole square into RL square. So this is the final equation. That means this is the magnitude of the output voltage that is calculated by the equation D, which is the charge sensitivity multiplied by the force applied. Omega is the frequency in radians per second. RL is the load resistance. Cp and Cl are the stray capacitance. Cp is the parallel capacitance, whereas the Cl is the stray or the load or the equivalent capacitance. So we had already found an equation VL is equal to V0 into WCP RL divided by square root of 1 plus omega square Cp plus Cl whole square into RL square. This is what we found for VL, the total value. Then let us consider some practical constraints. For example, in the case of for medium and high frequencies, definitely the value of omega is higher. As a result, this part become dominant than the 1, or you can say that omega square Cp plus Cl whole square into RL square become much greater than 1. As a result, this equation can be approximated as VL is approximately equal to V0 into omega Cp RL. This one become invisible. As a result, omega Cp plus Cl into RL, if you simplify, we will get the equation VL is approximately equal to V0 into Cp divided by Cp plus Cl. Okay, so with this we will conclude the piezoelectric transducer portion. So what is remaining is some application notes of piezoelectric transducers, which we are going to discuss in the coming class. Thank you for watching.